Hey everyone, welcome. You ever look at something simple and just wonder about the complex physics hiding inside? Well, today we're going to tackle a really cool puzzle. It looks pretty straightforward on the surface, but trust me, the solution is super elegant. Let's dive right in.
Okay, so take a look at this. We've got a simple hook, right? But it's being pulled on by two different forces. We'll call them P and Q. Now, each one is pulling kind of down and to the side, trying to drag that hook in its own direction.
And that right there, that's the heart of our puzzle. See, we're not just trying to figure out where the hook ends up. The real challenge is this. How can we get these two separate angled forces to team up, to combine into one single force that pulls perfectly straight down? How on earth do we make that happen?
All right, so before we can crack this thing, we got to know exactly what we're dealing with. So let's lay out the puzzle pieces. Okay, here's what we know. Force P is yanking with 75 newtons of force at a 20-degree angle off the vertical. Meanwhile, force Q is pulling at 35 degrees. So, the big unknowns, the things we need to find are, 1, how strong does force Q have to be? And 2, what's that final combined downward force going to be? We'll call that R for resultant. So, where do we even start with this? Well, the secret, the real trick, isn't to think of these forces as single diagonal pulls. It's to realize that each one is actually doing two jobs at the same time. This is going to be our big aha moment. Yeah, think about it like this. Force P isn't just pulling diagonally. It's secretly pulling the hook down a certain amount, and it's pulling it to the left a certain amount. And it's the same deal for force Q. It's pulling down, and it's pulling to the right. Every single angled force has these two hidden jobs it's doing. Now, in the world of physics, this idea has a name. We call them vector components. All it means is that we're splitting up a diagonal force into its two parts, the horizontal part and the vertical part. And the cool thing is, because those parts always make a nice right-angled triangle with the original force, we can use some basic trig, SOHCAHTOA, to figure out exactly how much force is going which way. And here you can see exactly what I'm talking about. On the left, you've got the original force P, right? But on the right, we can picture that same force as a team-up of a purely sideways pull and a purely downward pull. It's the exact same amount of total force. We're just looking at it in a way that's way more helpful for solving our puzzle. Okay, stick with me here, because this next part, this is the insight that just blows the whole puzzle wide open. So here's the deal. If we want the final combined force to be perfectly vertical, what has to happen with all that sideways pulling? Right, it has to disappear. It has to cancel out completely. It's got to be a perfect sideways stalemate, like a tug-of-war where neither side moves an inch. The leftward pull from P has to be exactly the same as the rightward pull from Q. And here's what that perfect balance looks like in math terms. Since our angles are measured from the vertical line, that sideways part, the opposite side of our little force triangle, we find that using sine. So the leftward pull is just P times sine of 20 degrees. The rightward pull is Q times sine of 35 degrees. And for that hook to go straight down, those two things have to be equal. Period. Yes. Okay, now that we have that key insight, we are ready to go. Let's solve for our first unknown, the exact strength of force Q. So here's the game plan. Step 1, we set those horizontal forces equal to each other. Step 2, we plug in the 75 newtons we already know for P. A quick tap on the calculator shows that P is pulling to the left with about 25.65 newtons of force. So to find Q, all we have to do is a little bit of algebra and rearrange that equation. And boom! There's our answer. Force Q has to be pulling with exactly 44.7 newtons. At that specific strength, and only that strength, its pull to the right perfectly cancels out P's pull to the left. We've done it. We have our sideways stalemate. The first half of the puzzle is solved. Awesome. So with all that sideways chaos perfectly balanced and out of the picture, we can finally get to the payoff. Let's figure out the total combined downward force. And you know what? This part is actually the easy part. It's beautifully simple. Since the side-to-side pulls are gone, what's left? Just the downward pulls from both P and Q. They're finally working together, like a team, pulling in the exact same direction. So to find that total force, R, all we gotta do is add them up. The process is super straightforward. The total force, R, is just the vertical part of P plus the vertical part of Q. Now this time, we're looking for the side of the triangle that's adjacent to our angle, so we use cosine. We just plug in the numbers we know, 75 newtons for P and that 44.7 newtons we just calculated for Q. That tells us P is contributing about 70.48 newtons downwards, and Q is adding another 36.62. You add those two numbers together, and we get our grand total. The final, combined, purely vertical force yanking down on that hook is 107.1 newtons. And just like that, the puzzle is solved.
So let's just do a quick recap. We started with force P at 75 newtons. We figured out that force Q had to be 44.7 newtons to get that perfect sideways balance. And once we did that, we found their combined downward pull, that big resultant force R, was 107.1 newtons. Simple as that.
And really, that's the big takeaway here. The moment you understand that you can break forces down into their component parts, you can start to control them. We engineered a perfect sideways stalemate. And by doing that, we channeled all the energy from two messy, angled forces into one single, powerful vertical pull. So I'll leave you with a question to chew on. This isn't just some abstract problem from a textbook, right? Think about the real world. Think about the cables on a huge suspension bridge, or the arms on a giant construction crane. Heck, even just two people trying to move a couch. Where else in your life do you see this principle? This idea of balancing forces to get exactly the result you want? It's everywhere once you start looking. Something to think about. Thanks for joining me on this one.